In this video, we're going to talk about the central limit theorem, and we're going to go through an example where we use the central limit theorem to find probabilities involving sample means. All right, so first, let me consider a distribution of x. Okay, so here I'm going to draw a distribution curve of x. Okay, and it doesn't have to be normal, it could be anything. So I'm going to go ahead and assume that it's a uniform distribution. Okay, so in this uniform distribution that I've drawn, x can take any value between 0 and 10. So any value between 0 and 10, and it is equal probability of being any number between 0 and 10. That's what it means to be a uniform distribution. Okay, so let's say x is uniformly distributed. Now, let's say I were to go and get a sample from this uniform distribution. So I were to go out and get a sample, and I were to calculate x bar, right, the sample mean. Now, the mean of this distribution is 5. It makes sense that it would be 5, right? It's halfway between 0 and 10, and every possible value has an equal opportunity being selected, so it seems reasonable that the mean of this distribution should be 5. So, I go out and I get a sample mean, and I calculate the sample mean using the sum of my sample values divided by n, right? And so I get this sample mean. Now I want to know actually what's the distribution of this sample mean. Now, what does it even mean to have a distribution of a sample mean? Well, so this is one sample mean, right? So I could have considered getting lots of different samples from this distribution. Theoretically, no one would actually do that. Usually people just get one sample, but consider theoretically I would get lots of different samples from this distribution, and I were to calculate the sample mean each time. Now, if I were to do that, I would expect that they're all going to be kind of close to 5, but they're going to be random. I mean, they're not going to be exactly equal to 5 because they're just samples, right? They're not. I didn't collect the entire population, so they're going to be randomly a little bit different than 5. Okay, and so these x bars, because they're random, they have a distribution, right? So the sample mean has a distribution, and so what the central limit theorem says. So by the central limit theorem, if n is large, so n being the sample size, okay, if n is large, then the distribution of x bars, the distribution of all these different sample means that came from your population, should be normally distributed, and it should be centered on the mean of the original distribution. So centered on mu, okay? All right, well, there you go. So that's what the central limit theorem says. And it says that the distribution of these sample means should be normal and centered on the original mean of the original data. And also it says one more thing, so that it should be centered there, but then also, so this distribution has its own variance, right? Its own standard deviation. It has its own mu and its own standard deviation. So its own population mean and its own population standard deviation. Okay, so what about this distribution? What's the standard deviation of this distribution, the distribution of x bar? Well, it's usually noted with this sigma of x bar. Okay, this is standard notation, and what this means, it's usually called standard error as opposed to being called standard deviation. So called standard error, and that's to say that it's the standard deviation of x bar. It's a standard deviation of a statistic versus a standard deviation of a random variable. Okay, so that's why we call it standard error and not standard deviation. Okay, but anyway, what it equals is sigma, so standard deviation of the original variable, divided by the square root of n. So divided by the square root of the sample size. Right, it makes sense that the standard deviation of all these sample means should be less than the standard deviation of the original data. All right, so one more thing I guess we need to know about central limit theorem is what does it mean to be large? Right? And it makes sense that n would have to be large in order for this result to hold, because imagine the extreme case where you only sampled one observation from the distribution. Right? If you only sampled one observation from the distribution, then when you calculate the sample mean, well, it's just going to equal x, right? Because you just calculated one. You just sampled one. So it would be the sum of that value divided by 1, right? Okay, well, if you were to do that, you were to sample 1, then you were to look at the distribution of those samples, you would get back to the original distribution of the data, right? So, obviously, n cannot equal 1. I mean, actually, n has to be large in order for this result to hold, in order for us to change from this distribution of a uniform distribution over to a normal distribution. Okay, well, so how large is large enough? Well, it depends a lot on the distribution of the original data, but a general practical rule of thumb is we say, well, if n is larger than 30, then n is large. Okay. All right. Yeah. Let's go ahead. Let's use this central limit theorem to answer a question involving probabilities involving sample mean. Okay. So life expectancy in the United States is a mean of 78 years old. Okay. So and a standard deviation of 10 years. Okay. Okay. So my random variable is going to be life expectancy, right? And the mean of life expectancy is going to be so mu 78 years old. Okay, and the standard deviation is 10. Okay, a sample of 36 people are selected. All right, random sample of 36 people are selected. All right, so I've selected n equals 36 people. Okay, find the probability that their average life expectancy is more than 80 years. Okay, so I need to recognize that this isn't the type of problem that we used to do where we would say, oh, okay, so the probability x is more than 80 years. No, this is not what this question is asking, right? It's not asking what's the probability that a randomly selected person, which is what x would be, the probability that, life expectancy of one person is more than 80. No. This question is saying, find the probability that their average, the average of these 36 people, the sample average is more than 80 years. It's asking us to find the probability x bar is more than 80 years. All right. So now, once we've noticed that, and we need to ask the question, okay, can I assume that the distribution of x bar is normal? Right? Because if I can't, then I can't answer this question, because it doesn't say that the distribution of x is normal. It doesn't give us anything about the distribution of x. As a matter of fact, the distribution of life expectancy is unlikely to be normally distributed, because people don't really die in a normal distribution around the mean. It's just like kind of a lump around your young ages, and then several more lumps around your later ages, those that are survivors of some acute diseases. Okay, so anyway, life expectancy, not normally distributed. So, is it reasonable that x bar is normally distributed? Well, so by CLT, by the central limit theorem, okay, x bar is normal. Why? Because the sample size is greater than 30. Okay, so because the sample size was larger than 30, we can make this assumption that by CLT, x bar is normal. Okay, so now when we know, we're like, okay, well, x bar is normal, and I'm trying to find the probability x bar is greater than 80. So let me go ahead and draw out what I know. Okay, so this is now going to be the distribution of x bar. Okay, and so in the center is going to be 78, right? Because remember, the center of the distribution of x bar and the distribution of x are the same, or the mean is the same. And okay, so I'm trying to find the probability x bar is greater than 80. So let's see, here's 80. 80 is about right here. Okay, I'm trying to find this probability right here, right? All right, so I'm going to need to do a transformation to the z, just like how I used to do. I used to take this to the distribution of z, and then I would use my table. All right, so I have some cutoff, and I have, where these two probability, these two areas are the same. I need to find what's the z value. All right, so remember the equation used to be, okay, so when I was trying to find going from x to z, just plain old x to z, I used to use this equation, z equals x minus mu over sigma. All right, so now I need to change this from being an x to being an x bar, right? And so this, instead of being mu, it needs to be mu of x bar and sigma of x bar, right? So we know that mu of x bar is the same thing as mu, and then sigma of x bar is sigma over the square root of n. So my new equation for z that I'm going to be using is z equals x bar minus mu over sigma over the square root of n. Okay, this is my new equation. All right, so let's go ahead and use this. So I'm going to be calculating the probability x bar is more than 80, and I'm looking for what this value of z is, right? I'm looking for what this value of z is right here. Okay, so let's see. I'm going to calculate the probability. I'm changing this x bar into a z. Okay, and I'm going from this 80 to some value of z, right? So 80 minus, now mu was 78. Sigma, okay, standard deviation is 10. 10. Square root of n, square root of 36. Okay, so now I just need to calculate this, and I can look at my table. I can try to figure this out. All right, so let's do it. Z is greater than, so this is 2 over 10 divided by 6. All right, let's pull out our calculator for that. So 10 divided by 6. Square root of 36 is 6, right? So that's 1.666. Okay, we should round that to at least 3 decimal places. So 1.667. All right, because we're going to round z to 2 decimal places. So we should round this denominator by at least 3. All right, so probability that z is less than, so let's see, 2 divided by 1.66. All right, so let's do it. 2 divided by 1.667. All right. 1.199. Okay, now I need to round z to 2 decimal places, right? Because our table has 2 decimal places in it. So that 9 brings that 9 to a 2. Okay, so that 1 to a 2. So it should be 1.2. All right. 1.2. All right, now if I go in my table, it's not going to tell me the probability that z is greater than 1.2, right? The table does not give the area in front of 1.2. No. The table gives the area behind 1.2. So whatever value I get in the table, I need to do 1 minus it, right? So I need to do 1 minus the value that's in the table. The table gives the less than. It doesn't give the greater than, it gives the less than probability. All right, so let's look up 1.2 in our table. Let's go ahead and pull out our table. Let's look up 1.2. All right, there it is, 1.2. All right, 1.2. Okay, so 0.8849. All right, let's go and write that down. So 0.8849. All right, 1 minus that. Let's pull out our calculator again. 1 minus 0.8849. 0.1151. 0.1151. All right, so there we go. The probability that the mean age of the 36 people that were randomly selected, the probability that their mean age will exceed 80 years is 0.1151.